My name is Howard Reeder. I'm the Managing Director of MESA, and we're going to be talking about this improved spectrum analysis and metrology with EMC cabinets. We're going to be giving this webinar in a few parts, but effectively I'm going to explain how it is that MESA Solutions and Shieldex got together. And Kim Petzold, who's on the screen with me, she's co-hosting from Shieldex's side. She'll be able to take any questions and answers. There's a Q&A button on your screen, which you're welcome to use. But I'm probably not going to be taking any questions during the session unless they're short. So if they're short questions, pop Kim a note and I can perhaps deal with those. I will, however, take questions towards the end in about half an hour or so, and gladly look forward to any discussion there afterwards. I'm going to give some background on spectrum analysis, which is benefited by having an EMC cabinet. I'm going to give some personal perspectives on the electromagnetic world around us. And this is important because it helps to explain why we use things like an EMC cabinet. We're going to use two case studies, which show some results which have used these cabinets. And then just to make it a bit more real for everybody, we're going to be doing a semi-live video demonstration. And then there'll be concluding remarks and some invitation for comments and questions. At this stage, let me just recognize that there are people in different regions of the world, so different time zones. I will try and speak more slowly as we go through, because there are different languages and cultures in the background. And I also wish to greet people who know me through my academic career, former students of mine, and business colleagues who've been invited and are on this call right now. So just to give some context as to why this is important. MESA Solutions was founded in 2002. We are an EMC and high-level metrology company working mostly on topics in South Africa. But in 2007, we had to work internationally, mostly with the Square Kilometre Array. We call that the SKA. It's the world's largest telescope in making, radio telescope. And the expertise we have goes back to the mid-1980s with both academic and technical activities. And our present main interests include electromagnetic compatibility, EMC, site characterization for the Square Kilometre Array in South Africa, electromagnetic interference, EMI, mitigation for small and large industries in this country and elsewhere. We do material dielectric property measurements, and we also run a lot of educational short courses in EMC and metrology because of my background. The relationship with Shieldex began with opportunities to use their excellent shielding materials, for example, to reduce the weight of a very heavy brass EMC cabinet that we were using without compromising any EMC properties. We'd like to show you about activities which require EMC cabinets. Now, there's quite a bit of work that we do in MESA. I'm just going to put a pointer onto this. There's quite a bit of work we do in sectors which have proprietary information, so I can't tell you much about it, but that would include the mining sector, the agricultural sector, our electrical network in general, industrial processing, the space industry, cell phone towers. Some things we can tell you about. If you look on the right-hand corner over here, we're often asked to look at electromagnetic interference coming from turbines, and particularly at the base of the turbine and at the nacelle of the turbine. We've been involved in flying drones around this, but we often make measurements on the ground. And when you make measurements on the ground, depending on whether the transformer is at the base of the turbine or the nacelle of the turbine, the information or energy coming out can be quite small. And if you stand 10 meters away and the energy is coming from the nacelle, it's very difficult to pick up that energy using normal sensitivities. You then really have to use a lot of preamplification and sensitive settings. And if you do that without an EMC cabinet, you have no chance of picking up energy from the turbine. We're doing a lot of work in South Africa particularly, but with the Square Kilometre Array in general on photovoltaics. And these passive photovoltaics, in other words, not tracking, produce quite a bit of noise, which gets onto cabling, it gets onto the systems which are connected in cabinets nearby. But if they are tracking, there's an incredible amount of noise which gets radiated from these systems, and we need to understand that, and we need EMC cabinets for this. This is a picture of a South African naval frigate, which we analyzed quite early on in the 2000s. We're going to mask out all the spectrum analyzers we used simply for proprietary purposes. But in this case, there were a couple of things which went wrong. One, there was coupling between our spectrum analyzer and antenna. Second of all, the antenna doesn't behave as it should inside a closed environment sitting inside of a naval frigate. Thirdly, there was energy coming from these devices over here, which was coming out on a current probe, and we weren't able to detect it with the system that we had there. Something which really does require an EMC cabinet is the square kilometer array. Now, this is a picture of the square kilometer array, and in the bottom left-hand corner, you can see some of these 13.5 meter telescopes, all of which have been designed by a company called EMSS in South Africa. And here is a view sitting on a mountain in our middle part of our country called the Karoo, looking at approximately 64 of these telescopes. And as we speak, they are being expanded. Down here at the bottom, we are making measurements of generator rooms for science organizations in this country. And when we're doing that, you can see we're using a log periodic dipole antenna array or current probes. But if we do not use these EMC cabinets, and here's a brass EMC cabinet, the sensitivities of measurement we're trying to make are just completely constrained. And this brass cabinet, which I'm referring to here, is the cabinet that we have replaced with this Shieldex cloth equivalent. Further activities that we've used EMC cabinets for are linked to, for example, a study of energy propagating in soil. And if you look at this picture over here, one of my former postdoctoral student groups, we were trying to analyze what happens if you've got cables in soil, and here they are on the right-hand side, they're in a schematic form. We put 2-meter coaxial cables underground at various heights, and we illuminated them with a signal generator and receiving the energy in this space you see over here. We then derived properties of the soil. We then analyzed electromagnetically what that was like. And this allowed us to characterize the kind of information that comes off cables when buried in soil for various installations. The bottom left-hand corner here, again, we've blanked out the spectrum analyzer we're using, but it's a very good spectrum analyzer. We were analyzing information coming from PV systems, which was put into some kind of cabinet, which then go into cables, which go into soil at some distance down, 1 meter down, 0.5 meter down, and then we covered that those cables with different levels of soil, half full, all full, and with various meshes. And we were looking at very careful studies of how energy propagated on those cables and soil, and you need an EMC cabinet for that. And this is one of the MESA Shieldex prototype cabinets. But to explain why you need to have all this in the first place, I think it's helpful to give some electromagnetic perspectives, and these are mine. This is stuff that I've done over the years teaching to postgraduate students, and I've got a lot of the information from people like Piet van der Laan, who I'm going to acknowledge shortly, from the Netherlands, who gave me these perspectives from their experience. What we've got here are 2 loops. These loops are about the size of your hand, and loop number 1 gets excited by a source at port 1. We use a network analyzer, but it could be a signal generator. It induces currents on this loop at various frequencies, 10 kilohertz, 100 kilohertz, megahertz, up to a couple of megahertz. And then there's a victim loop, something very nearby, where there's a lot of magnetic field and electric field coupling. And one of the studies that we do, and particularly with postgraduate students and also with EMC courses that we give, is to ask the question, if I want to stop the coupling from source to victim, would you prefer to use a thin-tinned circular plate, a square plate, or a rectangular plate? And it turns out, both by measurement and by computational study, and also by intuition, that in fact all of those plates do a good job. Whether you ground them or don't ground them, and whether you place them vertically or horizontally makes a difference. It doesn't make a massive difference, but it does turn out that this plate, put vertically, grounded, just about kills the coupling completely from quite a noisy source to a victim. Thanks to Ernst Berger, who was at EMSS at the time, now Altair, for doing this modeling for us. But you can see the picture. Energy on the right-hand side doesn't get to the left. Energy on the left-hand side does not get to the right-hand side if you see things in the right way. Here's another perspective on metrology and electromagnetics. This is a situation where we were analyzing Shieldex cloth. We were doing it because we needed to get good shielding materials from their cloth. They sent us samples, and we put these samples into a kind of a holder, which we placed above a cavity. Now, this is a book I wrote with a postgraduate student in 2000 on understanding microwave heating cavities. And if you look inside the book, you'll see some modes which can be excited if you place energy, like a magnetron, into a typical microwave oven. And here is one example of a mode. It's a 4-3-1 mode, and you can count the modes: 1, 2, 3, 1, 2, 3, 4, and then there's a quarter and a quarter variation, making a half, and that gives 1/2 variation. So it's a 4-3-1. When you place something in that cavity, like a dielectric, and we placed a dielectric in the corner over here, the modes change very, very quickly. And this is indeed what happens when you're in a reverberation chamber, when you're in your room, when you're in some kind of enclosure. The moment you get inside, you disturb the modes. And you can see the disturbing of modes from pure sine waves to these, or cosine waves, to the slightly more distorted picture. The reason this is important is that you then do not illuminate the material you're testing uniformly. You have various points where it's hot and cold. Just a perspective you should keep in mind. The last perspective I want to give in broad terms is that everything is coupled. This is a picture taken from a NASA probe on the far side of the moon, and the moon to the Earth, when you see it in this form, look like they're quite big objects, and indeed they are. If you try and do a calculation, you'll find that the moon and the Earth are capacitively coupled in the order of microfarads. And if you look at the moon and the Earth together, there are about 800 microfarads capacitors with respect to the universe. We're very, very intimately connected. So let's just give a case study one, because I'm speaking in abstract terms. Let's get quite specific. This is a prototype EMC cabinet that was developed by Shieldex and MESA. So we designed it, Shieldex had the material put together for us, and we're using these plastic supports to house it, and you will see various interfaces over here. What we were doing was analyzing a modern spectrum analyzer, and if you look at most modern spectrum analyzers, and I'm not going to say much about any one of them in particular, but many of them are just packed with features. And this is made possible by very high-speed processors. And in good instruments, what's happening is that hundreds of thousands of fast Fourier transforms are being performed per second. And this helps us to get these technical cutting-edge devices. And many of them claim very impressive high dynamic ranges, 100 dB, 120 dB of dynamic range. And they also claim displayed average noise levels, DANLs, of minus 100 dBm or lower. And this is really impressive, and it is achievable if you pay attention. These same devices have got very large touch color screens, because that's what customers want these days. And color streams are like electromagnetic apertures. They're almost transparent windows into your device. So the disadvantage of all of this is that you get self-generated EMI. So one of the things that we need to have an EMC cabinet for is that if you take a typical spectrum analyzer and you have an antenna, and the antenna is in any way coupled to the spectrum analyzer, for example, a meter or two apart, the radiation or the EMI from the spectrum analyzer itself gets into the antenna and then appears on the screen. So what we then do is we put the spectrum analyzer into this, what previously was a brass cabinet for us, very heavy and very difficult to move around the countryside, into this slightly more compact system, which is lightweight and collapsible, with an interface plate. And on the interface plate are coaxial connectors and power filters. So we put the spectrum analyzer in, and effectively that masks the antenna or the spectrum analyzer from the antenna. Of course, energy does go out backwards, but you need to be able to see the spectrum analyzer, and that's the price you pay. Now, when you do this experiment, this is a real experiment, and what we've done to clarify, we've just taken selected points, and these are no cheated selected points. These are genuine selected points. The type of energy from a typical spectrum analyzer of a modern kind you get is at this sort of level, between low frequency and 2 gigahertz. If you put it into this Shieldex MESA EMC cabinet, you'll see a reduction. And that reduction is really important to us. You will see the consequence of this shortly. The trouble with that previous experiment is that we're relying on the spectrum analyzer that we're using, and they all are different. So to make the experiment a little bit more controlled, we take the same EMC cabinet, we put a comb generator, which produces comb signals at 100 megahertz spacing or 200 megahertz spacing, from low frequency up to, say, 3 gigahertz in this case. And we switch the comb generator on, And to mimic the cable connections inside the cabinet going to the spectrum analyzer, we take a coaxial cable, which we connect to a shorted path, and we put an EMC current probe onto it, and we measure the energy through this interface on the spectrum analyzer, and we get a recording. So the energy in common mode current, that's current flowing on the outside of this coaxial cable inside the EMC cabinet, that energy from about 100 megahertz up to 3 gigahertz is that level. And then we measure the same thing, but this time with the current probe on the outside. And this current probe, just for your information, has got a bandwidth of 1 gigahertz, but we push the system up to 1 gigahertz for up to 3 gigahertz for illustration. And we take the coaxial cable, and just to represent a typical case, we put the coaxial cable lying on ground, and the ground, of course, has got capacitive connections back to our cabinets. This is part of the coupled universe I spoke about. And we measure position B, and we measure position A, and the difference between the two pictures are here. But just to summarize this, if we use the radiated approach, that's energy coming directly from a spectrum analyzer, where you have no EMC cabinet, and then you have the EMC cabinet, we find shielding values of between 20, 25 dB up to 2 gigahertz. With our cone generator approach, we find that we get shielding values which vary basically above 20 dB up to 3 gigahertz and more. Now, these variations here depend very, very much on the cable layout. So let's give you a second case study. This is maybe a little bit more interesting. What this case study was doing was to analyze emissions from a known source at a 10-meter distance. Now, let me give context to this picture. This is a picture I used to, or this is an environment in Stellenbosch. We're in the winelands of the Western Cape in South Africa. It's one of the bigger universities here. This is on top of the engineering building. And what I did with postgraduate students was to take a known level of emission on a cable, stand 10 meters away, which is a typical CISPA or IEEE or IEC measurement distance, and see what energy was picked up 10 meters away on a known antenna. To set the experiment up, we have a signal generator, we have a spectrum analyzer, but the spectrum analyzer typically has to be plugged in. So here it's plugged in over here, and then the cable runs approximately 20 meters back to a laboratory, and this cable forms part of the experiment. You can't get away from it. Everything is coupled. You also get reflections off the floor, and that is what open area test sites do. But it also turns out that this coil of power cord makes a difference, and this is the study that I present in a schematic form in this picture here. So let's look at the picture. We take a signal generator, and it's plugged into the mains. We have a variable attenuator here for reasons I could explain briefly, but we put a known signal level onto an antenna. And if you look at various books, this is a book from Jasper Goedbloed. He was the EMC engineer at Philips in Eindhoven. If you look at the picture of my camera, he was there in the sort of 1990s, 1980s, quite well known. And I met him when I was on a sabbatical at the European Space Agency in Noordwijk in the Netherlands. And what Jasper Goedbloed did in his book was he pointed out that if you take a typical cable of 2 meters long, and if you measure 5 microamps of current on both of the cable elements, in other words, cables currents flowing on the outside, we call that common mode current, you don't need to go for open area test site testing. You're already going to hit the limits. And Philips in the Netherlands never did conventional testing in those days. They just used these common mode current probes. So what I was doing was replicating this experiment where we created 5 microamps of current on this antenna or this cable at various frequencies in the megahertz range. We then went a distance of 10 meters. We physically placed a ground plane, physically put it there. And the reason for the variable attenuator was that sometimes the background noise was so high, it was easier to increase the transmission by 30 dB, which then increased the result in our spectrum analyzer by 30 dB, and I could correct for the 30 dB. But when I first did this experiment with postgraduate students, I didn't use an EMC cabinet, and the results were completely uncorrelatable. I could not show that 5 microamps of current on a resonant cable at say 50 megahertz, 60 megahertz caused 37 dB microvolts per meter of electric field 10 meters distance away, which is the limit for most CISPR standards. So if you look at CISPR 32, CISPR 11, they say you can produce 37 dB microvolts per meter for a Class B device at a distance of 10 meters, and you've passed the law. What Philips did was they said if you get 5 microamps of current on a cable, you will already be hitting that limit. So that's what we were testing. So why could I not get the results to work? And the reason I couldn't get the results to work was that the energy that I was transmitting was bouncing off the ground, it was going directly, it was landing on the spectrum analyzer and the cable going to the antenna, and the cable antenna, the antenna and the cable, the spectrum analyzer, the power cord, the coiling on the ground, all going back, all form part of the experiment. And so the results were just unreadable. I couldn't get good results. I then removed the cable to the spectrum analyzer and I got much better results, but I still didn't get the correct results. And that's because the coaxial cable and the spectrum analyzer form one big antenna. It's called antenna mode. And only when you put this into an EMC cabinet do you find that 5 microamps of current on a resonant cable 10 meters away produces 37 dB microvolts per meter. And that is what I used to do with the postgraduate students, measured, modeled, and actually discussed. Something which was I always enjoyed with the postgraduate students was that if you took that power cable, which was coiled, if you uncoil it, the results change by up to 1 to 4 dB. And the reason is that currents flowing on a power cable going through a coil system form capacitance to ground, and they form some kind of a coupled path here. If you pick the cable up and remove the loop, the cable forms a larger loop with your experiment, and the results change. So that tells you that whether you loop your power cord or not also makes a difference. So now this has been a little bit abstract, and you've got to, in a sense, believe me in all of this. I now would like to show you a video of an experiment which would be relevant to everybody. This is an EMC cabinet investigation. There's no special treatment here. Please watch the video and I'm going to talk you through it. So this is a spectrum analyzer. You don't know what class of spectrum analyzer. Wooden table. Here is the N-type connector. We've not grounded this in any special way. What we're now going to take is a 1 gigahertz current probe. This works from 10 hertz to a gigahertz. We're going to use an N-type connector. We've got 2 cables. One cable goes to the probe, one cable goes to the cabinet. You'll see that in a moment. And we're going to connect this all together where the N-type connector goes to the spectrum analyzer. We use a controlling laptop to control this spectrum analyzer, and this has got some material which one of my colleagues, Julian Drombolasson, wrote, software. And what we're doing is we're controlling the spectrum analyzer whilst looking at energy from the power cord going to the spectrum analyzer. So this is the controlling laptop. We've also put a computer screen which is connected to the same power supply but independent to the spectrum analyzer. So the first experiment is we take the coaxial cable to the current probe and we leave it dangling, connected to nothing on this table. And we'd like to have nothing being picked up. So we're going to start the measurement, and you're going to see the measurement appearing over here. And please notice the current probe is not connected to anything. What Jolie is doing is he's setting up the software to change the resolution bandwidth to 200 kilohertz. And here we see something coming from the current probe, recorded in maximum hold, which should pick up nothing because there's nothing going through it. However, energy on the cable, especially at cell phone frequencies and FM frequencies, get picked up by the outside of the cable. That's antenna mode. What we now do is we're going to take that and we place the comb, the current probe, onto the power cord going to our spectrum analyzer, and it lights up like a Christmas tree. This is all the energy that is apparently coming from the spectrum analyzer itself. What we then do is we put the current probe on the N-type connector right at the spectrum analyzer, and you see that the current power supply and the N-type connector information is very similar. And I'm going to make stills of these pictures in a while so you can see it more carefully. But I want you to notice now we connect the same current probe, which works over a gigahertz, onto the computer screen power cord. And you see it's much, much lower. That's the yellow trace. So the spectrum analyzer's power cord is producing a lot of energy. But is it everything to do with the spectrum analyzer? What we now do is we reduce the resolution bandwidth to 1 kilohertz. So in reducing the resolution bandwidth to a kilohertz, our noise floor is much, much lower, down at about minus 130 dBm, very, very low down. These are cell phone frequencies, these are FM frequencies, and the current probe isn't connected to anything. We then connect the current probe to the spectrum analyzer power cord and just look at the amount of energy on the power cord of the spectrum analyzer. I'll let you just look at this. This is on maximum hold. We then connect it to the input of the spectrum analyzer, and we see very similar high levels of energy right on the outside of the coaxial cable entering our spectrum analyzer. And let's record that. And you can see quite a noisy picture. And then finally, we're going to look at the energy on the screen power cable, and you'll see that's in the yellow trace now, much, much lower. It picks up the environmental cell phone FM, but also picks up a little bit of the noise from the spectrum analyzer. Now that's what happens if you do not use an EMC cabinet. So I'm going to stop that video. Now I'm going to take a second video where we are now going to be using an EMC cabinet. And I will give you a still of all these results in a moment. So here's the MESA Shieldex cabinet. We're just rotating it. You can see the interface structure. And here you can see a power filter. We've connected it to the power cord. We've got an N-type connector. We've got an SMA connector. We've got an earth cable, which we do not connect for this experiment. We're going to use the power filter to get rid of some of the energy on the power cord. And here is the adapter, the power supply to the spectrum analyzer, which we'll put inside the EMC cabinet for this experiment. Here we put the spectrum analyzer into the EMC cabinet. We then take the coaxial cable and we connect it to the spectrum analyzer, and then we connect the other side to the N-type connector at the back, and then we connect the coaxial current probe to the N-type connector at the back. So this is the setup now of the EMC cabinet. And we are leaving the EMC probe, or the current probe, which works from 10 to 2 gigahertz, disconnected. We have to show you how the instrument operates. So the spectrum analyzer's got a computer attached to it, slight weakness in this experiment. But the background noise, again, can you see we're picking up cell phone energy, which goes straight into the cabinet from this side. But none of that background noise is visible that you saw before. We've got rid of all that antenna mode stuff. Now we're looking at the same power cord. Can you see how much energy is being cleaned up? It's all being stopped by the EMC cabinet, and we're picking up a little bit of energy coming through the EMC cabinet, but some of it radiates out the side here. We now connect to the input of the N-type connector on the outside of the cabinet, and again, you will see we pick up the cell phone frequencies, television frequencies, FM frequencies. They tend to come inside the cabinet directly, but the picture is a whole lot cleaner than it was before. Now we take the current probe and we put it onto the screen power supply, and that's this yellow trace here on maximum hold. And you can see that it's just about completely cleaned up. We can't get rid of FM in the environment, and we can't get rid of the cell phone frequencies. Now, for the sake of resolution, we reduce the resolution bandwidth to 1 kilohertz, and now our noise level is just about minus 130 dBm. This is an incredible sensitivity. And you will see that our background noise is way, way down. And we pick up the FMs, the cell phones, you can't get rid of that. This is the charger itself of the spectrum analyzer. Yes, it's got some noise, which is just getting through over here, but this area of the spectrum is completely cleaned up. We're nearly done, and I'm going to show you this in still form. So let's complete with the current probe on the outside of the EMC cabinet. And finally, this current probe is going to go onto the cable to the computer screen. There it is there. And the yellow trace shows us just about no noise in these regions, and just the background environmental FMs, cell phones we can't get rid of. So that is a video to say to you, this is all genuine stuff. I'm not making this up and giving you nice schematic pictures. So we're just about done, and I'll ask them if there are any questions. Kim, could you confirm, have there been any questions in the chat so far?
No.
Okay, thank you. So I'm about to invite you to ask questions. This is the results from the videos. All I wanted to show you in the video was a real measurement made by my colleague Jolie Andrew using the software we use to drive a spectrum analyzer. And here in the top left-hand corner, using 100 kilohertz resolution bandwidth, the noise floor is just about at minus 110 dBm. There's the scale, minus 70 dBm, down to minus 130 dBm. We're over a gigahertz of bandwidth, which is our current probe. And the background noise, which you really can't get rid of, is the yellow trace. And this was the energy sitting on the power supply to the spectrum analyzer without an EMC cabinet. And then with an EMC cabinet, you see that all of that energy here disappears. In other words, this had nothing. This was a bad measurement. It was getting into the spectrum analyzer over the cable, straight into the touch screen and so on, and wasn't going through the RF port. So this, in fact, was a false measurement. Just to increase the resolution, we change from 100 kilohertz to 1 kilohertz, and you'll see the noise floor of the yellow trace drops down to nearly 130 dBm. When I was a kid, if I could have spectrum analyzers of that performance, it would have been revolutionary. We've come to expect it of modern spectrum analyzers. The trouble is, if you want to measure down to those levels of sensitivity, you cannot have your spectrum analyzer exposed. You need to put it into a cabinet. And here you will see where my cursor is. We make this a laser pointer. Here, if you look at my laser pointer, all of that noise is noise which does not enter the RF port of your spectrum analyzer. Let me give you an experience which frightened me. It frightened us because we ourselves know about the weakness of not using the EMC cabinet. This is a picture of 3 diesel generators, about 1.2 MVA, sitting in the Karoo in those telescopes that I showed you. And they're in a bunker which MESA helped to design the EMC properties of. What we're doing with these diesel generators, all of the walls are reinforced concrete where the reinforcing has been tightly put together. No cables enter this building or exit this building except at one point. And we put all cables from generators into cable trays or trenches. This is the best configuration from an EMC point of view of a diesel generator, and I would say anywhere in the world. This is in a radio astronomy site which is looking at the origins of our universe. We have to be quiet. What we were asked to do was to measure the energy from it. Now, we arrived on a Monday afternoon 2 weeks ago, and another colleague of mine, Kev Kutz, and myself, and Jolie Andrew quickly wanted to measure on day one the energy coming from the earth cable of the diesel generator. And what we measured here was this incredible noise. This is at minus 90 dBm, using a current probe on the cable going down to Earth, around about 140 megahertz, with these kind of spikes over here. We thought, oh my goodness, we cannot explain this. It just doesn't make sense. Why would that come from such a device? It was also in pulsed mode. We then said, we're not using our EMC cabinet. And so this very quick measurement was a mistake on our part. And so we slowed down, put this into an EMC cabinet, and then we saw this red trace. Absolutely quiet. There was nothing coming from this. What in fact was happening was energy was coupling onto the outside of this current probe, getting into the spectrum analyzer, going back on the inside of the cord to the cone, to the current probe, forming some kind of a coupled loop, coupling to the entire environment, and that's what gave rise to these resonances. They really were not real measurements at all. So this is something I should have learned as a kid, and I didn't, and I'm telling you, because even when you're experienced, you can make mistakes. Same thing with the radiated measurement. We used an antenna, and in this case, we used some of the Shieldex cloth on a stirrer to move the modal energy in this room to make it into a semi-reverberation environment. Without the EMC cabinet, we saw these same emissions around about the low 100 megahertz up to 150 radiating from this, but it was all to do with our exposed spectrum analyzer. When you put it into an EMC cabinet, we made the real measurement, which shows you the energy in these regions, which correlates with the common mode current. So this has taken me 35 minutes. That was the intention. I haven't given you an opportunity to ask questions. So I'd like to conclude, and I would ask you to feel free to ask questions.